We're looking at PriorVLA today, Prior Preserving Adaptation for Vision Language Action Models.
Yeah, it's a huge one.
It really is. So here is the core issue, right? Vision Language Action Models, or VLAs, they're incredibly powerful. But when we fine-tune them on limited downstream data, they suffer from this catastrophic prior forgetting.
Exactly.
They just lose their broad pre-trained knowledge and completely fail on out-of-distribution tasks. So PriorVLA solves this by updating only about 25% of the parameters.
Just 25.
Right. It freezes the original action expert to preserve those motor priors, and then it trains a parallel adaptation expert. And they use these attention-based expert queries to, bridge the results. A massive 22-point jump in out-of-distribution success on real-world robots using just 10 demonstrations. 10.
It's wild.
So welcome to AI Paper Podcasts. Today we're giving you a full breakdown of how this works.
Yeah, and I think this paper really forces us to completely rethink how we treat pre-training, not just as this starting point for our weights, but as a permanent read-only knowledge base.
Right, because right now that is not what we do.
No, not at all.
So let's dive into why the current standard practice-full fine-tuning is actually actively harming VLA models, like, P$Allers or OpenVLA.
Yeah, the trap of full fine-tuning, it's... The prevailing wisdom has always been to treat large-scale pre-training as just an initialization point. You grab this massive foundation model, and it basically places you in a nice, favorable spot on the lost landscape.
Sure.
And then what do? You apply full fine-tuning. You overwrite those weights using your very specific downstream data.
Which in robotics is usually super narrow.
Incredibly narrow. I mean, think about it. The pre-training data is astronomically diverse, right?
Yeah.
Millions of images, diverse physics, countless environments. But your downstream robot data.
It's like one specific lighting setup in one lab.
Exactly. A fixed camera angle, specific table textures, a handful of objects. So modern VLAs increasingly rely on flow matching, right, rather than simple discrete token prediction.
Okay, let's unpack that for a second for the listeners. Flow matching.
Right. So mathematically, the model is learning this continuous vector field, and that field transports a sample from a simple noise distribution to a really complex multimodal distribution of robot trajectories.
Got it.
And that vector field is shaped by the massive pre-training data set to understand broad physical concepts, like the inertia of a heavy block versus, say, the lightness of a sponge.
So intuitively knows physics.
Yes.
Yeah.
But when you apply full fine-tuning on your narrow data set of, picking up a white mug under fluorescent lights...
You're forcing it to forget everything else.
Exactly. You aren't just tweaking a final classification layer. You are forcefully bending that entire pre-trained vector field to overfit that one specific room. You destroy the out-of-distribution generalization.
Okay, let's unpack this with an analogy, because it's like hiring a Michelin star chef, right, to flip burgers at a fast food joint.
Aha! Yeah.
And after a week of full fine-tuning, they completely forget how to make anything but burgers. You've just, overwritten their foundational skills. They can't boil water or chop onion anymore.
That's a perfect way to put it. And the paper actually has the most striking evidence of this burger flipping amnesia, if we want to call it that.
The visual question answering analysis, right?
Yes, the VQA analysis. It's mind-blowing. So they took the base pre-trained VLA model before any fine-tuning, and they showed it a picture of a cat.
And it easily identifies it, I assume.
Perfectly. It says, this is a cat. They showed it the number 2 written in marker, and it reads the number 2. It has this incredibly robust, generalized understanding of visual concepts.
Right, because it was trained on millions of images.
Right. So then they apply standard full fine-tuning on a robot manipulation task. They just train the robot to move some blocks around on a table. After that fine-tuning, they ran the exact same visual test. They showed the cat again.
Yeah.
It spits out absolute gibberish.
Wait, really? It just can't see the cat anymore?
It literally forgets how to see and describe general concepts. Same for the number 2.
Yeah.
It's completely lost its ability to process the visual world simply because its weights were updated to move a robot arm.
That is wild. It just completely overwrites those priors.
And technically, this prior forgetting is why current models require massive amounts of diverse downstream demonstrations. If you erase the model's foundational understanding of the visual world, you now have to supply thousands of images of shadows, different lighting conditions, slightly different colored objects, just to rebuild its basic vision from scratch for your specific task.
So you're basically fighting the amnesia you just caused.
Exactly.
Okay, so that leads us directly to the paper's first major architectural shift, right?
Yeah.
If overwriting the weights causes amnesia, how do we train the model on new tasks without touching the original weights?
Right, how do you fix it?
And they do this through something called dual action experts, which is basically branching the brain.
Yeah, PriorVLA branches the pre-trained action expert, which again uses that flow matching setup we talked about, into two parallel tracks.
Okay, what's track one?
Track one is the prior expert, and this is the original frozen pre-trained model.
For no weights updated here at all.
Not a single one. It acts purely as a read-only source of motor priors. But here's the catch. Its actual final action output during denoising is completely discarded.
Thrown away.
Yep. Then you have track two, which is the adaptation expert. This one is initialized from the exact same pre-trained weights, but it is fully trainable. It handles all the downstream task specialization.
Okay, wait. I have to jump in here. Because if we are just running two massive models side by side and we throw away the prior expert's final output,
Yeah.
how does the trainable adaptation expert actually learn anything from the frozen one? I mean, they're completely isolated in the forward pass, right?
Right, they are.
So it feels like you've got this frozen model doing all this complex flow matching math for no reason, just to throw the answers in the trash.
Well, what's fascinating here is that both experts are executed along the exact same noisy action trajectory at each denoising step. But you're right, if they were completely isolated, it would be pointless. The priors would be trapped.
Right. So what's the bridge?
That's the paper's second major innovation, expert queries.
Expert queries. Okay, let's get into the connective tissue here, because this is the mechanism that answers my pushback.
Exactly. Expert queries are these learnable token interfaces applied via masked attention. They allow the trainable adaptation expert to basically read the internal representations of the frozen prior expert without actually merging their final outputs.
Here's where it gets really interesting, I think. It's essentially an open book test.
I like that.
Like the adaptation expert is the student taking the test, and the scene and motor queries are like sticky notes pulling exact paragraphs from the textbook, which is the prior expert, without rewriting the book itself.
That is a brilliant analogy, yeah. And there are three specific types of these query tokens we need to talk about.
Right, let's start with the scene queries.
So scene queries are inserted directly into the vision language model's input sequence, the VLM, right? So they go in alongside the image and text tokens.
Capture the visual stuff.
Right, to capture the task-relevant visual structure, the spatial relationships, depth, geometry. We call these scene priors.
Okay, and then you have the motor queries.
Yeah, motor queries. These are appended to the frozen prior expert to read its internal denoising representations, basically to extract the motor priors from the flow matching process.
But wait, if they're attached to the frozen expert, how do we stop the gradients from ruining the frozen weights?
That's a huge technical hurdle. Crucially, they use one-way cross-attention.
One way, so it doesn't corrupt the frozen pre-trained denoising path.
Exactly. During the forward pass, these motor queries act as the query in the attention computation, and the keys and values are derived directly from the hidden states of the frozen prior expert.
But the prior expert can't attend back to them.
Right. Any position where a token from the prior expert tries to attend backward to a motor query is masked with negative infinity before the softmax.
So the prior expert literally doesn't even know the queries are there. It's just humming along, computing his foundational physics.
Completely oblivious. Yeah, the flow of information is strictly one way.
Okay, so we pulled the visual structure with scene queries, we've pulled the physics with motor queries. Now what?
Now we have the third type, action queries.
Right, which live inside the adaptation expert.
Yep, inside the trainable branch. Their job is integration. These tokens integrate all those cached keys and values from the scene and motor queries to guide the final action generation.
Okay, so the trainable branch is basically learning how to ask the right questions.
Exactly. It's not memorizing physics from scratch. It's learning which physics priors are relevant to the current trajectory and pulling them in.
Man, that is elegant. But, clever architecture is academically interesting, but ML engineers care about empirical results. Does this open book test actually translate to better robotics? Because we need to look at the performance, which honestly speaks for itself.
It really does. First off, because they are only training the adaptation expert and these query tokens, PriorVLA updates only roughly 25% of the parameters compared to full fine-tuning.
Which is a huge computational win.
Massive. But the simulation results are where it gets real. On RoboTwin 2.0 hard...
Which is the out-of-distribution setting, right?
Right, lots of randomized lighting, distractors, that sort of thing. It improves over the TEPL5 baseline by 11 points.
Wow.
And on the saturated Lebro benchmark, it achieves an incredible 99.1% average success rate.
99.1. That's basically solved.
Pretty much. But, simulation is one thing. Real-world results are what actually matter.
Yes, let's talk about the hardware. They tested this on a single-arm Franca and a dual-arm AC-1 robot, right?
Yeah, across 8 different tasks, inserting pegs, sweeping blocks, hanging towels, all sorts of manipulation.
And with standard data, which is, 100 to 300 demos, it hits 81% in distribution and 57% out of distribution success, which is solid.
It's very solid. But here's the kicker, the few-shot performance.
Oh man, the few shot. So they reduced the training data to just 10 demonstrations per task.
Just 10, which in robotics is practically nothing.
It's absurd. You shouldn't be able to learn anything robust from 10 demos.
And yet, with just 10 demonstrations per task, PriorVLA hits 48% in distribution and 32% out of distribution success.
Which surpasses $10.05 by a massive 24 and 22 points, respectively.
Exactly. And let's be clear about what these ode perturbations were. We are talking altered lighting, novel background distractors, table height shifts.
The robot was put in environments it fundamentally had not seen during fine-tuning, and it still succeeded 1/3 of the time on just 10 examples.
If we connect this to the bigger picture, gathering high-quality teleoperated robot data is the biggest bottleneck in embodied AI right now.
Easily. It's so expensive.
It's horribly expensive and slow. So getting a plus 22-point boost on unseen environments with only 10 training examples, that is a massive leap towards scalable robotics.
It really is. It makes intuitive sense, too, right? If you only show a standard, fine-tuned Model 10 trajectories of moving a cup under bright lights, and then suddenly you dim the lights.
Some model panics.
Right, because you overrode its priors.
Yeah.
It hasn't seen a dim cup in its new fine-tuned memory, and it has no foundational understanding to fall back on.
Its vector field just collapses into noise.
But PriorVLA, because of those queries, it basically says, okay, the lighting changed, I don't recognize this visually, but hey, Prior Expert, the physics of a cup haven't changed, right?
And the Prior Expert says, nope, physics are exactly the same, and it stabilizes the denoising process.
That is so cool. Okay, but for the skeptical AI researcher listening...
There's always a skeptic.
Always. And they're probably asking, how do we know this isn't just the regularization benefit of having fewer trainable parameters? Like, keeping a huge chunk of the model frozen just acts as a giant regularizer that prevents overfitting.
Right, the parameter count trick argument.
Exactly. So let's dive into the ablations to prove the specific architecture actually matters.
Yeah, the authors anticipated that exact pushback. So they ran a series of ablations on a 6-task subset of RoboTwin 2.0.
Okay, what was the first one?
First, they tried removing the Prior Expert entirely, or essentially swapping it for a random frozen branch.
So keeping the parameter count the same, but removing the pre-trained knowledge.
Exactly. And when they did that, hard-ode success plummeted from 49% down to 42 or 43%.
So that proves the knowledge in the pre-trained weights is doing the work, not just the extra parameters acting as a buffer.
Definitively, yes. The specific mathematical representations of physics are necessary.
Okay, what if we just unfreeze the Prior Expert? Like, let the whole dual branch system co-adapt and train together.
They tried that too. Unfreezing the Prior Expert also degrades performance.
Because it drifts.
Yeah, exactly. Co-adaptation allows the model to drift right back into that prior forgetting trap. The representations shift to accommodate the narrow data, and it loses its broad stabilizing force. So a stable, untouched prior source is empirically superior.
That makes total sense. And what about the queries? What if we remove all the expert queries?
Performance tanks down to 28%.
Wow.
Yeah, the frozen branch is completely useless without the attention query interfaces to read it. They are completely bottlenecked.
It's like having the open book test, but the book is locked in a safe.
Exactly. And there is one more crucial ablation, freezing the vision encoder.
Oh, interesting. Did that help or hurt?
It hurt performance, which proves that while you want to preserve broad priors, visual specialization is still required.
Right, because it needs to adapt to, like, the specific camera intrinsics, the focal lengths of the new robot setup.
Yeah, you still need to see your specific environment clearly, even if you rely on broad priors for how physics works.
So what does this all mean? If we summarize all these ablations,
it means PriorVLA successfully decouples prior preservation from task specialization.
and it proves you need both. You need a pristine memory bank and a specialized learning module to succeed in the real world.
Absolutely.
Okay, we are wrapping up our deep dive here, and I want to crystallize the value for the listener's own ML projects.
Yeah, the main takeaway.
Instead of viewing foundation models simply as weight initializations to be overwritten, which is what we've all been doing, we need to treat them as rich, queryable knowledge bases during downstream adaptation.
It's a complete paradigm shift. And it actually leaves us with a really provocative thought for the future.
Oh, I like provocative thoughts. Let's hear it.
Well, think about it. If we can successfully extract specific motor and scene priors via attention queries without modifying the base model at all, could we eventually build dynamic prior libraries?
Wait, dynamic prior libraries, like swapping them out?
Yes. Imagine a robot operating in a factory. Instead of trying to train one massive VLA that holds every single skill, you build a system that hot swaps different frozen pre-trained experts on the fly.
Oh, wow. So like the robot approaches a sink and it dynamically routes its expert queries to a frozen fluid dynamics expert.
Right, and it pours the water perfectly. Then it turns around and needs to stack some heavy boxes.
So it just drops the fluid expert, hot swaps to a frozen rigid body expert, and routes those exact same query tokens to the new textbook.
Exactly, simply by routing the expert queries during inference. No retraining required, just handing the student a different textbook.
That is mind-blowing. Hyper-specialized foundational priors deployed as read-only cartridges. That could completely change embodied AI.
It really could. It's an incredibly exciting direction.
Well, you've definitely given us a lot to think about today. Thank you for listening to this episode of AI Paper Podcasts. We'll catch you on the next one.